Okay, our topic now is to relate the electrical work, cell potential, and delta G naught. In our previous discussions, we learned how to determine the cell potential of a galvanic cell. Okay, and we know that a galvanic cell can generate electricity because it makes use of a spontaneous redox reaction. So that electricity is actually your electrical work. And we know that work is related to the Gibbs energy from chapter 17. So now, if we look at that electrical work, work is practically the cell voltage or the electromotive force multiplied by the charge carried by the electron. Now, why did I say that? Remember, from the anode to the cathode, there is a potential difference. That's why electrons are traveling from the anode to the cathode, because of the difference in the reduction potentials of these two substances. So we have a net pull of electrons toward the cathode. So it creates a voltage or the electromotive force or the cell potential. But remember that the moving particle is charged. That's why we need to multiply by the charge to get the work done. Okay, so practically your work is equal to the E naught of the cell multiplied by the charge carried by the electron in this case. Now the charge have been figured out for us before. Remember, an electron carries a 1.6 times 10 to the negative 19 coulombs. We learned that from trimester 1. And then since we're talking about moles now, we can convert that into a quantity that we can relate better. And Faraday's constant already gave that to us. That's 96,485 coulombs per mole of electrons. So we're not talking about a single electron here, but a mole of electrons. So it amounts to as much as 96,485 coulombs. Therefore, we arrive at an expression work is equal to the E cell multiplied by N, which is the number of electrons, multiplied by the Faraday's constant. Okay, now since we know that delta G naught is equal to the maximum work that a chemical system can perform aside from the expansion work through the pressure volume expansion, this is actually your electrical work. So the maximum electrical work that you can get is defined by this expression. But since our electrochemical system is the one doing the work, therefore that work is negative of NF E cell. Again, because the system is doing the work. So energy leaves the system. So we are now having this relationship between the cell potential and the Gibbs energy of the system. We know that a spontaneous reaction under standard conditions is negative, and therefore your E cell is positive for spontaneous processes. Our equation tells us that. Okay, and in chapter 17 we also related that for non-standard conditions. What do we have? Delta G is equal to delta G naught plus RT ln of Q. So under non-standard conditions, delta G is equal to negative of NFE. Under standard conditions, delta G naught is negative NFE naught. So if we substitute that here, we'll end up with saying negative NFE is equal to negative NFE naught plus RT ln of Q. So if we simplify this, dividing everything by negative NF, all the terms, will end up with what is known as the Nernst equation. Okay, over NF here, ln of Q. Remember that Q here is our reaction quotient. Okay, so again, refresh our memory. R that we're using here is 8.314 joule per mole per Kelvin, so that we can have direct access to the joules. N is the number of moles of electrons involved in the electron transfer. And of course, F here is your Faraday's constant, which is amounting to 96,485 coulombs per mole of electrons. So you see here, if we look at the relationship of the units, so just we're not lost. The Gibbs is in joule, right? Faraday's constant is in coulombs per mole. You have mole of electrons here, and your cell potential is in volts. So it tells us that 1 joule is essentially 1 coulomb volt. So that's the work of Faraday. He's also the one who named the anode the cathode that we use now for our voltaic cell. So let's continue. The Nernst equation can be reduced into a smaller type of equation if we set at equilibrium. What do we have? At equilibrium, our Q becomes our KQ, and such our cell registers 0 volt. Okay, in as much as our delta G becomes 0 the same way. So when your cell potential becomes 0, your battery is dead, so it's already in equilibrium. So our equation reduces to E naught is equal to RT over NF ln of Q. Okay, so now we have a relationship between the standard cell potential and, let me just change, that should be KQ now. Okay, between the cell potential and the equilibrium constant. So we can now try applying this equation with a problem that we have. So let's look at this one here. It says here, use the data in the reduction potential table above to calculate the equilibrium constant at 25 Celsius for the reaction. So we already know how to construct a galvanic cell here. Nickel is oxidized to nickel 2+, so that will be our oxidation half reaction. We know that the nickel solid gets oxidized to nickel 2+, and 2 electrons have to be released. So if we look at our reduction potential table, this is reduction in this case, so we flip the sign here because we're using this as an oxidation, so that's positive 0.26 volts. And then silver gets reduced, that's a regular reduction here, so that will be 2 silver ions taking up those 2 electrons, forming 2 silver solid with a reduction potential of positive 0.8 volts. Therefore, our cell potential under standard conditions would be, what's that? 1.116 volts. And now, from our previous derivation, we said that the E naught of the cell can be computed from RT over NF ln of KQ. So we just have to substitute values. Our calculated E naught is 1.16 volts. Our R is 8.314, that's joule per mole Kelvin. Under standard conditions, that would be 298 Kelvin. Over here, it's important to note that 2 electrons are involved in the transfer. Okay, the reaction is balanced here, so that's 2 electrons here, 2 moles, and Faraday's constant is 96,485 coulombs per mole, and therefore that's your ln KQ. So KQ would be equal to what? So we are expecting a value larger than 1, and probably a large value because the voltage is high enough, 1.16. So let me just work on my calculator. So that's 1.16 multiplied by 2 multiplied by 96,485 divided by 8.314 divided by 298. So it's like what? That's 90.3486 is equal to ln of KQ. So if we take E of both sides, so we'll end up with this. What's that? Wow, that's a large number. 1.73 times 10 to 39. Okay, there you have it. So again, what did we do? If we can calculate the cell potential under standard conditions, we have direct access to the equilibrium constant using Nernst equation. Remember, Nernst equation says E is equal to E naught, okay, minus RT ln of Q over NF. But since at equilibrium, again, E becomes 0, so your E naught becomes RT over NF ln of KQ. Okay, so there you go. So we'll stop here for now, and we will continue with the application of the Nernst equation in another video.